Good morning, everyone. So today I will go through a few problems with you about the chapter number 4. It's basically about the two-dimensional motion, two or three-dimensional motion, and about the circular motion. Those are the applications. So you'll find in this document So first of all, we have one example. I called it example to differentiate it from the other problems. This given is not in the book, so that's why I called it example. And then all the other problems, they are from the book, okay, with the figures as well. So let's start with the first one. I will read the given and then we're going to, again, write it on the whiteboard and then solve it together. A particle with velocity v0 equals minus 2i plus 4j in meters per second at t equals 0 undergoes a constant acceleration, a, of magnitude a equals 3 meters per second squared at an angle theta equals 130 degrees from the positive direction of the x-axis. What is the particle's velocity v at t equals 5 seconds? So that's question. So first of all, here when you see this I with a hat, it means that this is the unit vector, you know, for the x-axis, and the same J with a hat, it's the unit vector of the y-axis. We don't write them in this notation, but they are the same. So they say that we have that this particle, it has v0 at initial time t equals 0, and it's moving under constant acceleration. And be careful here, the constant acceleration is a vector. So A is constant in magnitude and in direction. So it has magnitude 3 meters per second squared and angles 130 degrees. And it's from the positive direction of the x-axis. Now the question, what is the velocity? Let me share my screen, my tablet screen, so we can solve them together on the whiteboard. Voilà. So let's start. I will actually read the given and then we'll write what we read on here on our notebook. So we have a particle. This is the example number 1. What is called example 1. So the particle has a velocity v0. So we have a particle with a velocity v0 equals minus 2i plus 4j. At the time, so all of this is at t equals 0. So this is at t equals 0. Okay, voila. And we know that this particle, it undergoes a motion under a constant acceleration, which is a, where we have for this vector a, we know that the magnitude is 3 meters per second squared, and we know that the angle theta is given by 130 degrees. And when they say so, they said that this angle is from the positive direction of the x-axis, which means that if this is the x-axis, this acceleration, it makes an angle in this way. So this angle theta is with respect to the positive x-axis direction. Okay. What is the particle's velocity v? So the question is, what is v at the time t equals 5 seconds? This is the question. Okay, let's see what do we have. So we need to get the equation of the velocity v. Now, do we have some particular characteristic of this motion بتخولنا انه نستعمل الايكويشنز اللي نحن بنعرفهم يلي جبناهم ب chapter 2 قلنا انه they are valid in the case of two-dimensional motion? Actually, yes, it is the case, because in the given he said that the particle undergoes a constant acceleration, which means that we can apply the kinematic equation, and what we need is the v as a function of time. So we need v as a function of time, but of course we are talking about the vector v. So if you have a look at the slides, you will see that this vector v, it's nothing else than v0 plus a t, where v0 is the initial velocity vector, which is also given here. It is given by v0 equals 2i plus 4j. And the acceleration is as well clear. It's A equals to 3 meters per second squared for the magnitude and with a given direction. So let's actually do it. What we know about this equation is that we can write it down projected along x and projected along y. So along x, we know that Vx as a function of time, of course, it's given by V0x plus AXT. And we know that along y, we can write down Vyt is equal to V0y plus AYT, right? Now, we know what is V0x and V0y. You see here in this equation of V0, we have V0 equals minus 2i plus 4j. So V0x is minus 2 and V0y is 4. But the question, what are AX and AY? Okay, that's very simple. We know that this is the vector A, right? And we know that this vector, it has two components. It has the angle theta, for any angle theta. Here the figure is for any angle theta. We can actually make the projection. So you go from the vector and then you start to make a perpendicular along the x and the y axis. So you end up with the component AX and here with the component AY, okay? Now, how can we get AX and AY as a function of A and theta? It's the following. Let's write down here aside. Let's write down cosine and sine theta. So if you just take this angle theta, cosine theta, it's given by the adjacent, which means here is the adjacent, that is AX, divided by the hypotenuse, the magnitude of the vector A. So from here, we can conclude that AX is equal to A cosine theta, right? And in the same way, we can also deduce that if you just write down sine theta, so you see here, sine theta is actually the opposite divided by the hypotenuse. So it is AY divided by A. And so from here, we can deduce that AY is equal to A sine theta. Okay? So all what we have to do now is to deduce Vx as a function of time and Vy as a function of time. So let's do it. Then Vx as a function of time is equal to V0x is equal to minus 2 plus Ax is equal to A cosine theta. So plus A cosine theta. So it's equal to minus 2 plus A is given by 3 and cosine 130 degree. And so this gives us the value, this is AX times time. So we still have the time in here. So this is the time. And so it's equal to minus 2 minus 1.93 t. So this is the expression of the velocity Vx as a function of time for its x component. Now we have to do the same for the Vy. So let's do it. Vy as a function of time, it's given by, so V0y, it's plus 4, plus Ay, it's given by A sine theta multiplied by the time. So it's equal to 4 plus 3 multiplied by sine 130 degree multiplied by the time t. And this gives us the value. So it's given by 4 plus 2.3 t. And this is Vyt. So now we can write down V as a function of time as Vxi plus Vyj. We need to evaluate the velocity at a given time that is t equals 5 seconds. So let's do it. Now we can write down V as a function of time, which is the vector. It's given by, so it's Vx as a function of time, I plus Vyj. So V as a function of time evaluated at the time, at the time 5 seconds, it's equal to, so let's have a look. Vx, here it is in the first one, so it's equation number 1. And Vy is equation number 2. So we have to write, instead of Vx, the equation number 1 at time 5 seconds, we end up with minus 2 minus 1.93 multiplied by 5 along x plus, instead of vyt, we are going to write down equation 2, evaluated at 5 seconds. So we end up with 4 plus 2.3 multiplied by 5. And this is along the y-axis. And so we end up with minus 11.64 I plus 15.49 J, and of course in meters per second. So this is the velocity in the vector actually notation, we can call it. The vector v at t equals 5 seconds is given by this value. We can actually, for example, deduce the modulus or the magnitude of this vector, which is given by square root of vx squared plus vy squared, and that gives us square root of minus 11.64 squared plus 15.49 squared, and that gives the value 19.4 meters per second. Okay. We can also determine the direction of this vector v. So we can write down, we can always write down tangent theta is given by vy divided by vx. Okay, so whenever we want to determine direction, we can always write down tangent theta equal to the ratio between the y component divided by the x component of a given vector. So we can deduce that theta is equal to arctangent or tangent minus 1 of vy divided by vx, and that gives you the value. So it's arctangent of plus 15 divided by 49 divided by minus 11.64, and so we get the value theta equals minus 53 degrees. Okay. Now we have one comment about that. So that's the answer that we get in principle for the theta. But have a look. This actually value of the angle, you know, let us think about v as this kind of vector. So if this is x and this is y, as we have taken, this theta means that we are going down with respect to the x-axis, and we expect the vector v to be in this location. But actually, if you look at the vector v at the time t equals 5 seconds, you see it, and it's over here. It's minus 15.64 I plus 15.59 J, which means that our vector velocity, it is like that. It has a negative x component, which means that it's pointing in the opposite direction with respect to x, right? And so this is Vx basically, and Vy it's positive, which means Vy is pointing upward. So we can actually deduce that the vector V should be pointing in this direction. This is our vector V at the time t equals 5 seconds. So actually this angle given by minus 53 given by this tangent is not correct. In order to get the correct direction of this vector velocity, you have to add to this minus 53 80. So you have to add to it pi basically. And if you add to it pi, you end up with the correct angle, which is 127 degrees. Okay, so in other words, because you know tangent theta and tangent pi over 2 minus theta is pi plus theta, they give the same value. So it could be that this angle is correct, or you have to add to it pi or subtract pi from it to get the correct direction of V. So in this case, actually, then we can deduce that this is not the correct value of theta. Theta should be equal to this minus 53 plus 180, so that we can get the right value, which is 127 degrees. So that's it for this example. Now we are going to move to the first problem. I will read it, and then we are going to write the given. So I will go on now. So let's call it, this is the problem 8. Problem 8. A particle initially located at the origin has an acceleration of, so when they say that it's initially located at the origin, that means that R0 is equal to 0, right? So it has 0x and 0y at the origin. It has an acceleration of a equals 3j meter per second squared, and an initial velocity, and also has v0 of 5i meters per second. Now we have to find in the part A, you have to find the position and the velocity at any time. That means you have to find r as a function of time and the velocity v as a function of time. So they don't say vector. Yeah, they say vector, but even if they don't say vector, you have to deduce by yourself, since you know this, the a and v. So a is along the y-axis and v is along the x-axis. It means that this object is moving in 2 dimensions. And the second part, you have to find the coordinates and the speed of the particle at time t equals 2 seconds. So what is r at t equals 2 seconds, and what is the velocity v at t equals 2 seconds? Okay, let's go on. We have the acceleration in here. So the first question is the acceleration constant or not? And it seems that the acceleration is constant. It's given by plus 3g meters per second squared. So we can apply the kinematic equations. We can simply apply and use kinematic equations that we have already for 2-dimension motion case. What do we know about it? So we know, for example, that in this case, v is equal to, so we know that v is given by, let's start with the v. So we know that v as a function of time t is given by v0 plus at. So what you can do here is simply that you can add each vector as it is. So v0 is given by 5i, and a it's given by 3j multiplied by t. And so actually we can simply deduce that this vector velocity v is given by 5i plus 3j meters per second. And this is the velocity. Let me just correct in here, just put it so that it's clear enough. So this is the vector I. And so this is the velocity. Now, what about the r? We know that r as a function of time, it's given by half a t squared plus v0 t plus r0. And don't forget that all of them, they are vectors, right? So we know that r initial, or this r0 is equal to 0 because it's in the given, actually. This is 0, so it disappears from the equation. And we are only left with what we have in here. So what do we have? We have half a, it's given by 3j, as we have seen, t squared, plus v0, it's given by 5i. And so we end up with the vector position r as a function of time. It's given by 5t, or even let's start from the beginning. So it's given by 3/2 t squared along the y-axis plus 5t along the x-axis. And so this is the position as a function of time as required, and this is the velocity as a function of time as required. And of course here r is expressed in meters. Now the second question is, how much is the position and this velocity at a given particular time, which is t equals 2 seconds. So now we know everything. All what we need to do is to just replace each term by its value. So v at the time t equals 2 seconds, it's given by 5i, it does not change, plus 3 multiplied by 2 along the y-axis. And so it's given by 5 plus 6. So it's equal to 5i plus 6 j. Okay, now you can determine the magnitude of the vector v as given by square root of 5 squared e 25 plus 6 squared e 36, and so we end up with 7.81 meters per second. So this is what concerns the acceleration, the velocity. And we can also in the same way evaluate the position at the time t equals 2 seconds. So it's given by 3 over 2 multiplied by 2 squared along j plus 5 multiplied by 2 along I. And so we end up with 2 and 2, they cancel out. So we end up with 1 of this one and 2 cancel out. And so we end up with 6j plus 10i. And of course in meters. So we can actually deduce that this is x, so this is x at time t equals 2 seconds, and this is nothing else than y at time t equals 2 seconds. Okay, so that's it. Even if you have an acceleration that is constant along only one dimension, that means that and you don't have anything else like in this case, that means that, for example, like in this case here, so a is equal to 3j meters per second squared. It means that the acceleration along the y-axis is equal to 3, and the component along the x-axis is simply 0 because it does not exist. It's not in this equation. So you can think about it this way. And as you have seen in here, in this equation, we have simply replaced each vector by its expression, and it's over. Once you do things properly, then everything is solved in a very easy way. Let's continue with another problem now. So we continue with problem 35. I will read the given, and then we are going to write it on the tablet. So you have a figure, which I'm going to draw here. It's actually a circle. You have at a given point here, so you have a vector, which is the vector v. Okay, this v should be, of course, tangent to the circle. We have also a vector a, which is the vector acceleration according to them, and this is the radius of the circle. And they say here they have written a equals to 15 meters per second squared, and they put here the angle, which is given by 30 degrees. Okay. So I will read the given. They say that this figure represented here on my whiteboard represents the total acceleration of a particle moving clockwise, which means that it's moving in this direction, the particle, right? Clockwise, it means in this direction. In a circle of radius 2.5 meter at a certain instant of time. So the radius of the circle is given by 2.5 meters. And this figure that you have in here, it only shows the motion of the particle at a given time, instant time. Now, at this instant, at this particular instant given and defined by this figure, you have to find in A, the radial acceleration. So what is AR? In part B, you have to find the speed of the particle. So what is V? And in part C, you have to find its tangential acceleration, which is AT. So those are the questions. This is all what we know about this motion. All what we know about it is this figure. You have the vector V, you have the vector A here, which makes an angle 30 degrees with the radius. The radius of this circle is 2.5 meters, and the acceleration, the total acceleration. So he said that this is the total acceleration. It's given by 15 meters per second squared. So what is AR, what is V, and what is AT? Now, we have to make some analysis before to start. So if I ask you what is AR, I think everyone will say AR is equal to V squared divided by R. And that is correct. But the problem is that we know r, it's equal to 2.5 meters, but we do not know what is v. The speed is unknown, and it is what we have to determine in the second question. What that means that we cannot use, so we know that AR is equal to V squared divided by R, but the problem is that this quantity is unknown. And we have to determine it in part B. So that means that this equation cannot be applied here because simply V is unknown. What do we have to apply then? We have to check what do we know about the acceleration in general. So actually there is something very important in this problem. In the given, we are told that this vector A, it is the total acceleration of the particle at the instant shown in the figure. And we know what is the value of this vector A. And we also know something very important, in that this vector, it makes an angle 30 with respect to the radius. So if we make the projection, we know that the radial acceleration, it's the acceleration along the radius. And so if we make a projection of this vector r along the radius, we can simply deduce the radial acceleration. It's over there, right? So this is AR, basically. Now let's call this angle between the A and the radius theta. Then you can see simply that cosine theta, it's given by the adjacent, which in this case AR, divided by the hypotenuse, which is A. So هي السايد اللي لازقة فيها divided by the hypotenuse. And so from here we can simply deduce that AR is equal to A multiplied by cosine theta. So as you can see, A is known and theta is known. So all what we have to do is just to replace each term by its value. And so we end up with A is given by 15 multiplied by cosine 30. And that gives us the value of 13 meters per second squared. So this gives 13 meters per second squared. So this is AR. This is the value we have to determine. Okay. Now, the second question was, what is the speed of the particle at that instant? How to determine the speed of the particle? This was difficult in the, before passing through part A. But now, actually, we can simply use what we've been discussing before. We know that AR, by definition, is given by V squared divided by R, where V is the instantaneous velocity. So V is the instantaneous velocity. That means V is the velocity of the particle, so the speed, the magnitude of the velocity of the particle, instantaneous, at the time for which A was equal to 15 meters per second squared. Instantaneous, so it's to be more rigorous, I should say, V is the instantaneous speed, is the instantaneous or the magnitude of the instantaneous velocity. We have AR. We just have simply calculated before. We know what is the R. So all what we have to do is just write down V squared equals AR times R. And so V is square root of R times AR. So it is given by square root of 32.5, and that gives 5.7 meters per second. Okay. Now the final question is now, how much is the A tangential? That's not very complicated, actually. However, you have to always think about what you have in your hands. So what we know, for example, from the definition, as we have seen them in the, so this is V, actually. Let me just write down, this is V. Now, we have seen actually in the class that the tangential acceleration, it's given by the derivative of the speed with respect to time, right? However, here we don't know anything about that. All what we know is that we have just derived the instantaneous speed is given by 5.7 meters per second, and we do not have any expression for this speed. So how can we determine it? Actually, let's check what do we know about the particle at this instant. So we know v, the value of v, but we don't know what is the expression of v. We know the total acceleration a, and we know the radial acceleration ar. Okay, that's already a good piece of information. So we know a and ar are known. But actually this expression of v is not known. So in principle, we cannot use this definition in this part. However, what we should use is the following. We know that the total acceleration a is given by ar plus a tangential, right? And we have seen that the modulus of a, the magnitude, is given by ar squared plus a tangential squared. So we can simply write down then a squared is equal to ar squared minus at squared. And you see we have an equation that relates ar, and a tangential. So we can write down a tangential squared is equal to a squared minus ar squared. And so we can simply deduce that a tangential is the square root of this expression, ar squared, and so it's square root of 15 squared minus 13 squared, and that gives the value of 7.5 meters per second squared. So that is the tangential acceleration that we were looking for. And as you have seen in this, for example, kind of problem, we did not use at all the definitions of the tangential acceleration to get them. We only used the definition of the radial acceleration to access the instantaneous velocity, because the instantaneous velocity is either accessed through evaluating the expression of the v as a function of time at a given time, but otherwise we have to look for a formula to evaluate it. However, for the ar and a tangential, we simply used, what we know about the vectors in this case. So for example, we know that the vector a, it makes an angle theta with the radial direction. And so we thought that a simple projection of the vector a onto the radial direction gives us the radial component. And then later on, to get the tangential acceleration, we simply use the fact that total acceleration is equal to ar plus at in vectors, as we have written. And so simply a squared is equal to ar squared plus a, pardon, there's a plus. So plus at squared. Okay. Yeah, that's it for this problem. Now let's move to another problem, which is problem 36. So problem 36, I will share with you the document, and then we're going to go again to the tablet. So problem 36, it has the following given. A ball swings in a vertical circle at the end of a rope 1.5 meters long. When the ball is 36.9 degrees past the lowest point on its way up, its total acceleration is minus 22.5 I plus 20.2 J meters per second squared. The questions are, at that instant, described by the previous numbers, sketch a vector diagram showing the components of its acceleration, then determine the magnitude of its radial acceleration, and finally determine the speed and the velocity of the ball. Okay, so let's share now the tablet and then write down this given in terms of numbers. Okay. So let's write it down in terms of numbers. First of all, let's read again the given. So a ball swings in a vertical circle at the end of a rope 1.5 meters long. So let me start. This is problem 36. We have a ball, and this ball is, so this is the ball, okay? This ball is attached to a rope, and the length of the rope is 1.5 meters long. So its length is 1.5. Now they say when the ball is 36.7, so let's say that we have an angle theta equals 36.9 degrees, past the lowest point on its way up, so we can simply understand it this way. So this was the ball, okay? It was on its way up, so it was actually moving, and at this point in here, it passes its, so at this point in here, it passes its lowest point. So the lowest point is over here. Now, after it passes this point and making an angle theta, this is the angle theta, okay? So that is theta angle. And making the angle theta with respect to this minimum position or lowest point, its total acceleration was given. So at this angle theta, the total acceleration was given by minus 22 I plus 20.2 J meters per second squared. Okay, so in part A, we have to sketch the diagram showing the components. So we have to sketch, let's just say it in this way. Sketch A on the figure. In part B, we have to determine the magnitude of its radial acceleration. So what is AR? And in part C, we have to determine the speed and the velocity of the ball. So that means what is the value of the instantaneous velocity and what is the direction of the instantaneous velocity. That's what they mean by the speed and the velocity. Okay. Well, okay. So let's actually start. First of all, it's very easy. We need to sketch the vector A. This is not very hard. Let me just correct this. So 36.9 degrees. Okay, at this point, the acceleration was given by the following expression. So let's write down, or let's draw A. So first of all, we need to take the X and Y coordinates. So we take them conventionally, X to the right and Y upward. Okay, and now let's draw the A. So as you can see, AX is given by minus 22I. That means that actually AX is pointing to the left, so in opposite direction with respect to the x-axis. So that is AX. And let me check the value. So it's minus 22.5. Okay, it's minus 22.5 here. So minus 22 minus 22.5 I. So this is AX, and AY is given by 20.2 J. So the AY is pointing upward, just like the y-axis, and it's given by this value. So this is AY. This is AX, and this is AY. That's number one. Number two, what is the component? What is the radial acceleration? Given that this is what we have. We have this is AX and AY. Now, how could you get the radial acceleration? You have actually two ways to understand this. So first of all, you can write it in this way. Okay, you can say this is AX and this is AY. Okay, those two vectors, they have projection along the radial acceleration, right? And so the addition of these projections, they define together a R. So in other words, you can say the following. Part B, you can say that AR is given by AX r plus AYR. So the projection of x along the radial direction and the projection of AY along the radial direction. Now, what concerns AX, this is all about vectors, right? And the projection of vectors. So let's actually put them correctly together. This is AX in here, and this is AY. So the angle theta, which is here, it becomes over there. So this becomes the angle theta. Okay, because they are just opposite angles. So this angle becomes pi over 2 minus theta. This one, it becomes pi over 2 minus theta, right? And so let's make the projections. So we can simply write down AR equals AXR plus AYR. So it is equal to AX times cosine pi over 2 minus theta plus AY times cosine theta. And if we just replace each term by its value, what do we end up with? So we end up with 22.5 cosine 90 degrees minus 36.9 degrees plus AY, which is given by 20.2 multiplied by cosine 36.9 degrees. And so this overall gives the value of 29.7 meters per second squared. That's all. Okay. So another way to see this for those who cannot really understand it, we can write it in this way. So we know that in general, the vector A, it can be written as AX along the along the x-axis plus AY along J, right? And this same vector A, it can be written as AR along the radial direction plus A tangential along the tangential direction UT, okay? Now, how to go from one basis to another, you have to write one in terms of the other. So it means, so this you can think of it as the vector AX plus the vector AY, okay? Now what you can do is the following. One can write, okay, AX and AY, okay, in the polar coordinate system, in polar coordinates. So how can we do it? We can simply say that AX could be equal to AX projected along R, UR, plus AX projected along T, UT. In the same way, AY is the projection of AY along the R direction UR plus the projection of AY along the tangential direction times UT. And so now if you simply write down A as AX plus AY plus AY, you will end up with the following. So you would end up with AX R U R plus AXT UT plus AYR UR plus AYT UT, okay? And so since it's a vector sum, you have to put all the terms together that belongs to the same axis. So if you have here UR and UR, those two gives the same, those two terms, they can add it up. And so we can write down this is AXR plus AYR UR. And you can also look at the terms that are along the tangential acceleration. And so you can simply write down plus AXT plus AYT UT. Okay, and so this is along the radial direction, and this factor is along the tangential direction. Now, what we are looking at, we need AR, so this is nothing else than ARUR plus ATUT. So you see, AR is nothing else than AX projected along R plus AY projected along R, and for the tangential component, it's gonna be AX along T plus AY projected along T. And so this is what we did basically. First, we did here. We said that AR is nothing else than AXR plus AYR, and then we have done the projection of AX along the radial direction and that of AY along the radial direction, and so we end up with this result. Is 29.7 meters per second squared. So that was the second question. Now the third question was, how much is the speed and the velocity of the ball at this instant as well? Okay, how much is the speed? Let's start with the speed because it's easy to deal with. So part C, how much is the speed and the velocity? Okay. In what concerns the speed, we know that AR is equal to V squared divided by R. Okay, so we can simply deduce that V is equal to square root of R AR. Okay, now R is known, it's given by 1.5 meters because it's nothing else than the length of this rope, right? هي عمليا طول الحبلة، لأنه إذا كانت الحبلة هي اللي عم تبرم والطاوة معلقة فيها، فعمليا وكأنه هي عم تمشي على circle والراديوس تبع السيركل هو طول الحبلة نفسها. AR we have just evaluated previously, so we end up with square root of R that is given by 1.5 meters multiplied by 29.7 meters per second squared, and that gives the value of 6.67 meters per second. And so this is the value of the velocity. Now, how is this velocity directed? We definitely know that this velocity, I will draw the figure again here. So this is the rope, okay, and the ball was here at this point. So going from its lowest point. So this is the angle theta. We know that actually the vector V is all the time tangent to the direction of the motion, right? So actually we expect that this vector V, and it's actually going, this ball was going up. So the vector V is pointing in this direction. And that is the Von V. It's actually along the tangent to the circle, and it is 36.9 degrees above the horizontal. So in other words, if I just want to write it, so this is the vector V. If you consider the horizontal at this point, this angle is nothing else than the angle theta. Okay, so we can say that V is tangent to the circle and it is at theta equals 36.9 degrees above the horizontal. That's it. Okay, so let's go on with another problem. So we are going to stop here, and later on we are going to make further problems so that the video will not be too big. So that's it for this video.